Alright, hello class. In this particular video we're going to be talking about directional derivatives and the gradient. And so this looks to answer the natural question that we have, which is, alright, given a surface and say we're sitting at a point, we can find the derivative in the positive x direction, right? That's f sub x. And we can find the, say, steepness of the surface in the positive y direction, that's f sub y. But what if we wanted to find the derivative in this direction? Okay, or maybe we wanted to find the derivative in this direction. Right now, if the surface is nice and continuous, we would expect that it's somewhere in between these. Right, the value would be, like if this is 5 and this is -5, this might be 0 or something in between. But how do we actually find it, right, explicitly? All right, so that's the main question here, right? Which is, how do we find the derivative or steepness in any direction we want? All right, and to answer that, first we need to talk about what's called the gradient. Okay? Okay, so the gradient of f is a vector that we use to help us find derivatives of surfaces. So specifically the gradient, and here's the notation we use, it's an upside down triangle. The gradient of f, okay, is the vector f sub x comma f sub y. Okay, so to talk about what's going on here, this triangle is actually an operator. Okay, it's a vector operator which puts the partial derivative with respect to x in the x component and the partial derivative with respect to y in the y component. And that's 2 dimensions. We can also have a 3-dimensional version, which would be the partial derivative of x in the x component, of y in the y component, and the partial with respect to z in the z component. And you can have, you can go as far as you want, right? As many variables as you have, this gradient operator is going to act this way. And what the gradient actually is, ends up being, it's essentially scalar multiplication. I shouldn't put a dot there, but it's essentially scalar multiplication, because we have the vector, which is the partial derivatives in our vector, and we're multiplying it by the function f of xy. So it comes out to be the partial with respect to x of f of xy and the partial with respect to y of f of xy. Okay? Or simply f sub x comma f sub y. Okay, so that's the gradient. Now, what the gradient is, it's analogous to the normal derivative in Calculus 1. Okay, so let's think about all the things that the derivative gives us in Calculus 1. So Calculus 1, right, we talk about if y is equal to f of x, then the derivative dy by dx is f prime of x. So there are quite a few things that the derivative gives us. For one, it is the slope of the tangent line of y at any x. Okay, that's one thing. Right, which also essentially gives us the steepness of the curve. Okay, at that point. There are a couple other things that the derivative can do for us, right? When f prime of x equals 0, that's a critical point, right? And that's where we have possible maxes and mins. Right, and specifically, it's the rate of change of y in the direction of x. Okay? Well, it turns out that in Calculus 3, it's not any partial derivative that gives that to us. It's actually the gradient. So it's the gradient of f, which is the vector made up of all the partial derivatives that we have, out to z if we have it, or w or whatever, however many we have. And this is what gives us all of this information. Okay, but we're going to talk about that because we're going to show how this all works as we go forward. But this is analogous, or it's the analog, okay, of f prime, just in 3D or multiple dimensions. Okay, so everything we sort of know about the derivative is going to be essentially true for the gradient versus the partial derivatives themselves. Okay, so an important question is, what does the gradient give us? What is it? And specifically, at any particular point, the gradient points in what's called the direction of steepest ascent. Okay, so what is the direction of steepest ascent? Well, what that means is the gradient of f, right, points in the direction okay, where travel would be at its steepest. Right, so in other words, it points in the direction where we have the highest possible rate of change. So in other words, if you're standing here, and if you could travel this way, say you'd have, let's say f sub y is 5, and in this direction, let's say f sub x is 5, but say halfway in between, this derivative is 10, and that's the highest, right? This is the direction that the gradient would point in. Okay, so I think it's actually easier to show what we're talking about with an actual example. So I'm going to prepare that, but I want to also get across some of the vocabulary before we do. All right, so as we mentioned, the gradient f gives the direction of steepest ascent. The magnitude of the gradient is the actual rate of that ascent. You can think of this as the measurement of the steepness in that direction. Right, and it's basically what the highest steepness possible is from that point. Okay? Now if we negate it, negative the gradient is the direction of steepest descent. Well, okay, if you can travel in this direction and get 10, right, so if we look at it from the side, let's say, right, we travel this way to get the highest ascent, this direction is going to give us the steepest descent. And again, this will be easier to see once we get to a three-dimensional graph. And then any directions perpendicular to the gradient are directions of no change. And again, this will be a lot easier to talk about with an example. So let's just look at an example. Okay, so let's look at this particular example. We're starting with a fairly simple one. f of xy is equal to 3 plus x squared plus 3y squared. All right, so this is going to be a paraboloid. Actually, yeah, this is going to be a paraboloid that opens upwards. All right, it should be a paraboloid that opens upwards, and we want to look at the gradient at this point too, negative 110. So specifically, the gradient itself is going to be the vector f sub x comma f sub y. Okay, so we're just going to take the x derivative, which will just be 2x, and the y derivative, which will be 6y. Okay, if you're curious where this point came from, I just picked 2 and negative 1 and put it into here, which will give you the 10, okay, for your z. All right, now at the point 2, negative 1, now notice we don't put the 10 in here because 10 is the z value that we get out here on the surface itself. So that point is on the surface here, but the gradient is just a two-dimensional vector. Okay, so that means we're looking at this surface from above and talking about the direction of steepest ascent, say, in terms of what direction you should travel, like left, right, up, down, north, south, etc. Okay, so when we plug in 2, 1, we're going to get the vector 4, negative 6. All right, so this is the direction of steepest ascent. Okay, so let's go to the graph and actually see what that means for us. All right, so here's a graph. Okay, here's the surface, here's the point we were looking at. Okay, and then here is the level curve that goes to that point. So this is the z equals 1, or sorry, z equals 10 level curve. Now, if I plot the gradient, you can see that it is, well, kind of a very large vector. So let me instead look at this one. So this is the same direction, I've just shortened it a little bit so it's easier to manage. Okay? Now if we look at this from above, what this is telling us is that if we're standing at this point, this is the direction we would want to travel in to get our steepest ascent. Okay? Now if I match this direction, okay, on the surface itself, what this shows me is, yeah, here's the direction that we would travel along the surface itself, which would be at the steepest. And note that only works at this particular point. But if this is the direction of steepest ascent, then this, down this way, is the direction of steepest descent. Okay? Now, here's what I meant when I was saying that any direction perpendicular to the gradient is going to be a direction of no change. So here is a line that is perpendicular to the gradient. Okay, I pick both sides, and you can see that this direction lines up and is tangent with the level curve. So what that's saying is that when we are sitting at this point here, we need to travel in this direction to move at the steepest direction that we can up this bowl. However, if we go perpendicular to that, we're going to be walking along this level curve. And walking along a level curve, it's in the name, it's level, right? The z is not changing along this level curve. So that's what I mean by direction of no change. That when you travel perpendicular to your direction of steepest ascent, you're going to be just not changing your z's at all. Okay? Now, when I will actually take the magnitude of this, right? Take the magnitude, that will give me 4 squared plus negative 6 squared, square root of all that. So that'll be square root of 16 plus 36. That'll be the square root of 52, right? Which is about 7.2-ish. All right, so what that means is this steepness, as steep as this ascent would be, would measure about 7, whereas this would measure about 0. Okay? All right, so that is what the gradient gives us as far as direction of steepest ascent, descent, and direction of no change. Okay, so sorry for the bright white screen here, but I also have prepared this pre-done graphic here, this particular surface here for x e to the negative x squared minus y squared, and we see we have a dip down into a bowl and then a hill. Okay, so when we look at the contours, so here are all the contours of that surface at different z values, and then here are some gradients. Okay, and you see here at this point it's pointing up towards the top of the hill, and depending on you know, wherever you might be standing, so here when we're in the greenish part, we're pointing you know, away from the bottom of that bowl. Here we're pointing towards the top of the hill. Okay, now here is gradient at just various different points. And one thing you can see is that the gradient is always perpendicular to level curves, because the level curve is the direction of no change, and the gradient is always perpendicular to the direction of no change. Okay, so as you can see, wherever point we are, we're pointing towards the top of this hill. Okay, or in here we're pointing out of the bowl. Okay, same thing here, and here we have the gradient and just more points, pointing up towards the top of the hill, pointing out of the bowl, and you'll notice here that this vector is much longer than this one. So if we scroll up here, that's because this is a much steeper climb in this area than it is up here. In fact, it starts to shallow out a little bit as we get closer to the actual top of the hill. That's what this is telling us. Not only does it tell us the direction of steepest ascent, it lets us quickly see and compare those rates of ascent, right? This is a much steeper area here than here. Okay, and you can also see that based on how close level curves are together. It makes sense if all these level curves are really close together, that's going to be a steeper climb than when they're further apart, right? This is a very steep area here versus here, and that's because each one of these is a jump in z of, it looks like 0.1. Okay, and these are closer together, so we make a jump of about 0.4 here, whereas it takes us this much to jump another 0.4. Okay, so that is graphically what the gradient gives us. Now, how does this help us with finding directional derivatives? And that's what we're going to look at next. Okay, so the directional derivative of z equals f of xy in the direction of the unit vector u. Now we need a unit vector for this to work. At the point AB is given by this formula here. It is, and here's the notation I like to use. I like to say it's the partial derivative of z with respect to u. So I'm basically saying I'm taking the derivative of z in the direction of u, okay, is, well, it's going to be the gradient of f at the point AB dotted with the vector u. Okay, so this may seem like an interesting or maybe an odd thing here. It's just the dot product of the gradient and the direction. Okay, so there are a couple things that we need to talk about here. One, remember that the dot product, right, v dot w, remember it gives us the amount of push one vector applies to another in its original direction. Right, so it measures the amount of push v, so v dot w measures the amount of push v gives to w in w's original direction. So that means the gradient of f dot u, that's going to measure how much the gradient gives in that direction. So the gradient of f dot u, this gives, we can think of it as the amount of derivative the gradient gives in the direction of u. Right, because if, let's say, u equals x comma y, and this is only going to happen if, you know, the magnitude is equal to 1, okay, then the gradient of f dotted with u, okay, is going to be, well, it's f sub x comma f sub y dot x comma y. Okay, so that means it's f sub x times x plus f sub y times y. Right, so it's x is how much of the x derivative we get, and y is how much of the y derivative we get. Right, this is, it's actually a pretty neat result. And it turns out what is actually really fascinating about it is, remember, the dot product can be written completely in terms of cosine and the angle, right? So this could be the magnitude of the gradient at AB. So that's the measurement, right? That's the full measurement of the steepness times the magnitude of u times cosine theta, which is really just going to be the magnitude of f times cosine theta, where theta is the angle between the gradient of f and u. All right, so before I do any examples, what I want to show you is that what we get if, say, my u is I. So I, remember, is the vector 1, 0. So this is the unit vector in the x direction. Okay? So if I take the gradient, so let's say I want the directional derivative of f in the direction of I, that's going to be the gradient of f dot I. So that's going to be f sub x, comma f sub y, dotted with 1, 0. When we take this dot product, it's f sub x times 1 plus f sub y times 0. And look at that. That's just f sub x. Remember, we already established that this is the derivative of f in the x direction, right? And if we do the same thing with j, right, which will be the magnitude of f dot j, not the magnitude, sorry, the gradient f dot j, that will be f sub x comma f sub y dot 0 comma 1, which will be f sub x times 0 plus f sub y times 1, which will end up being just f sub y. So we already see that this formula works in the positive x, positive y directions to give us exactly what we've already established. Okay? What's interesting is if we start looking at other directions. So for example, let's think about the unit vector, let's say 1/2 comma square root of 3 over 2. Right? This is the vector representing (30 degrees). Or, no, actually, that should be 60 degrees, right? Right, because cosine of 60 is 1/2, sine of 60 is root 3 over 2. Okay, so if we take the directional derivative of f in the direction of this particular u, again, like always, it's the gradient of f dotted with u. So it will be f sub x comma f sub y dot 1/2 comma 3/2, or root 3 over 2. Okay, so what that means is we get 1/2 times f sub x plus root 3 over 2 times f sub y. All right, which gives us about 0.5 times f sub x plus 0.87 times f sub y. All right, now if we go back to the example we looked at before, this 3 plus x squared plus 3y squared, and here we have our gradient, which is 4, -6, at the point 2, -1, okay? And we can actually start looking at directional derivatives of this function in relation to the angle that it makes with the gradient. Okay, so what ends up happening is we know that the rate here is 7.2, and we know that if we're perpendicular to the gradient, we should get a directional derivative, okay, of 0. So let's see. Anything perpendicular, right, is going to be 90 degrees, essentially. And so if this is our unit vector, u, then the partial of f with respect to u, right, is going to be the magnitude of f times cosine of pi over 2. Well, cosine of pi over 2 is 0. Okay? And if we did 3 pi over 2, that would take us all the way back to here. It would be the same thing. Or negative pi over 2, the same thing. Okay? So now if we go 45 degrees, right? So let's call this V. which will be 45 degrees from F. Let me do it in a different color here. So that will be pi over 4. The directional derivative of F in the direction of V will be the magnitude of the gradient times cosine of pi over 4, right, which will be root 2 over 2 times 7.2. All right, which is about 5.09. All right, so we start here at about 7.2. We reduce down to 5.09, halfway between, then to 0. Okay, then let's see what happens if we get to 3 pi over 4 away. Okay, so let's actually do that in red. Okay, so this will be the directional derivative of F in the direction of W, and so it will be the gradient of F times cosine of 3 pi over, not 2, sorry, 4. Okay, so 3 pi over 4, so cosine, this will be in quadrant 2, it will be negative. And so it will end up being negative 5.09. So now we've swept from 7.2 to 5.09 down to 0 to negative 5.09. And then if we go all the way to pi, right, a full 180 degrees away, let's call this L. It'll be the magnitude of the gradient times cosine pi. Well, cosine pi is -1, so that's going to be negative 7.2, which makes sense. If it's positive 7.2 in this direction, it will be negative 7.2 if you go the opposite way. Right? You'll be going downhill in this direction, and then it will sweep back up. Okay, so here I have graphed in orange the gradient, right? This is the full gradient. And here I have a unit vector, and for each unit vector that I'm going to sweep around, I'm going to show the directional derivative in the direction of that. So here it starts at 7.21 and then starts to sweep down until we get perpendicular when we'll hit 0, and then we'll start hitting the negative values, and then around to negative 7.2, and then we flip back around and we're going to increase up to 0. There we go, and back around to our 7.21. Okay? So if we go back to the surface, whoops, here we go. That should make some sense, because as we sweep around, well, we'll sweep from our 7.2 down to 0 here, and then we'll sweep back around to 0, right, to the negative value, then back up to 0, then back to the 7.21. Okay, so this is essentially how the directional derivative works, and I find this actually quite a nice result. Actually, it's actually kind of fascinating that the directional derivative is just the dot product of the gradient in whatever direction you want. Okay, if you don't use a unit vector, though, you're going to mess things up, because if you have a magnitude if we go back to the formula, here, if we don't have a unit vector, then this is going to adjust the amount that you get of the full steepness, right? This is the full steepness, and then cosine theta tells you how much of that full steepness you get, right? Whether it's 1 for 100% or 0.5 for 50, 0, etc. All right, so let's actually do another example with some math, because we can't always look at a graph, but we can always use the math that we've learned to figure this stuff out. So given the function f of xy equals x squared times e to the x minus 5y, let's find the direction of steepest ascent of f at the point 5,1. So that will be part A. Then part B, let's then find the directional derivatives of f at 5,1 in the direction of the vectors v, which is 1, 1, and w, which is negative 1, 3. Okay, so first of all, direction of steepest ascent, we need to find the gradient. Okay, so the gradient of f, that will be the vector made up of f sub x and f sub y. Okay, so f sub x, when we take the x derivative, this is going to be a product rule, right? So it'll be the derivative of the first, which will be 2x, times the e stuff left alone, right? Then plus the first guy left alone, the x squared left alone, times the derivative of the second guy. So that's going to be e to the stuff times the derivative of the inside with respect to x. So I'm going to write it out like this. Derivative of x will be 1. The derivative of 5y will be 0. All right, so there's that derivative. Now for the y derivative, thankfully, there's actually no product rule to do here because we just have the x out front, which will be a constant. The only y's we have are inside of the e stuff. So the derivative will be just x squared, then e to the stuff times the derivative of the stuff, which will simply be, in this case, 0 minus 5. And I'm just going to put this like this, e to the x minus 5y. Okay, so the simplified version of this I'll put here. It will just be 2x e to the x minus 5y plus x squared times e to the x minus 5y, comma, negative 5x squared e to the x minus 5y. Okay, making sure I have everything. There we go. So now, this looks kind of complicated, and I want to show you a trick that is actually really helpful. Notice how every term here has an e to the x minus 5y, and they all also share an x. We can actually factor all of this out of the vector itself. So we can take out an x and an e to the x minus 5y, and then just write what we have left, which will be 2 plus x in the first component and a negative 5x in the second component. All right, this is a little trick that will be very helpful in a lot of vector-based problems when you're dealing with variables. Okay, so here's the gradient. Now, we want the direction of steepest ascent at the point 5,1. All right, so let's plug in 5,1 into our gradient. Okay, so the x value is 5. Okay, and so we'll have 5 minus 5 times 1, and this was chosen specifically to make this e to the 0, which will go to 1. Right, then we'll have 2 plus 5, comma, negative 5 times 5. So we'll get 5 times 7 comma negative 25. All right, which will be the vector 35 comma negative 125. Okay, which is going to be, well, that's a very large vector. Okay. All right, so on the graph here, if this is the point 5, 1, here's the gradient, and which makes some sense. We're talking about 35 and negative 125. So that's you know, it's a very, very high magnitude for the vector. So let's get ourselves something a little easier to look at by taking the unit vector of it. Okay, so I'm going to call the vector g for gradient, the unit vector in the direction of the gradient itself. So that's going to be the vector 35 comma negative 125 all over the magnitude of the gradient, which will be the square root 35 squared plus negative 125 squared. All right, so that doesn't come out to be very nice. I went ahead in a calculator and got that this is about 0.2696 comma negative 0.930. Okay, there we go. That's a much easier vector to deal with and to kind of see what direction we're talking about. So that is the direction of steepest ascent for the surface at that point. Okay, and now it wants us to find the directional derivative in the direction of two vectors. So if we go back here, first is the vector 1, 1, and next is the vector negative 1, 3. Now, those vectors are not unit vectors, so we need to actually unify them, so to speak. So that's what we're going to do. Okay, so let's call u1. That's going to be the vector in the direction of 1, 1. Okay, so it will be the vector 1, 1 divided by the magnitude of 1, 1, which is the square root of 1 squared plus 1 squared. So that is 1, 1 over the square root of 2, which if you rationalize this, this is going to be the vector square root of 2 over 2, comma square root of 2 over 2. This actually corresponds with a 45-degree angle, or pi over 4 radians. Okay, so that's our u. Then our u1, our u2 will be in the direction of the other vector, which there we go, is negative 1, 3. So this will be the unit vector in that direction. So it'll be negative 1, 3 over negative 1 squared plus 3 squared, square root of all that. So it's going to be negative 1, 3 over the square root of 10. Okay, so that's going to be the vector negative root 10 over 10, comma 3 root 10 over 10. Now this part isn't 100% necessary, but you know, it also doesn't hurt. Okay, and here they are on a graph just to see what we're talking about. Here's the direction of u1, here's the direction of u2. Now you'll notice u2 is extremely close to the actual gradient, just in the opposite direction. All right, so let's calculate the directional derivatives in these directions. Okay, so the directional derivative of f in the direction of u1 is we take the gradient at 5, 1. So we're looking at this point. Right? This is the pointwise thing. And then we're dotting it with the vector u1. Right? So this will be, so our gradient vector you can kind of see it up there. It's 35, comma, negative 125, right? And we're going to dot it with square root of 2 over 2, comma, square root of 2 over 2. Okay, so this will be 35 times root 2 over 2 minus 125 times root 2 over 2. Right, which is going to end up being negative 45 times the square root of 2. Okay, so that is about negative 63.64. Okay, so that's the directional derivative in that direction. And if we look at the graph, that actually does make some sense because if we think about what would be perpendicular to the gradient itself, we've passed that, right? We've spun past that, and we should be on the negative side now. Okay, we didn't actually calculate the magnitude. Oh, we did. I just didn't write it. The magnitude of the gradient, right, is about 129.81. All right, so this would be about 129 going in this direction, and what we found in this direction for U1 was about negative 63.64. Okay, now let's do the directional derivative in the direction of U2, which is done the same way. We take the gradient, we dot it with U2, and in this case U2 is this vector here, negative root 10 over 10, comma 3 root 10 over 10. All right, so it will be negative 35 root 10 over 10 minus 125 root 10 over 10. Whoops, I'm sorry, that's not right. It's negative 375. Okay, which will come together and give us negative 410 root 10 over 10. Well, when we divide through by the 10, it will be negative 41 times root 10, which is going to be approximately, okay, which comes out to be about negative 129.65, which we'll see is very close to the negative of this, just a little smaller. This is 129.81. This is negative 129.65, which is what we expected. These are very close to being parallel, but this is in the opposite direction. Okay? All right, so that is pretty much what there is to talk about regarding directional derivatives and the gradient. So in the next lecture, we are going to talk about what else the gradient does for us in terms of max and min problems. Okay, so